Determination of the electrochemical series. The objective for this experiment is to determine the standard cell potential of several electrochemical cells. The standard cell potential, it's a measurement in voltage, that's the unit, and it's a standard measurement because we're taking those measurements under specific conditions. Those conditions are considered standard conditions. 298 kelvins, which is about room temperature, atmospheric pressure, and then if you're using concentrations, which we're going to be using solutions, the solutions that we're using, they have a concentration equal to 1 molar. The electrochemical cells, we have different types of electrochemical cells, but the ones that we're using in this experiment are galvanic cells, in which you actually have a spontaneous reaction, redox reaction happening, and a potential is generated because of the transfer of electrons. So we're using redox reactions or oxidation reduction reactions. When you have an oxidation reduction reaction, you have your two processes happening at the same time. Something is being oxidized, something is being reduced. Your redox reactions are this type of reactions where electrons are being transferred. So your electrons are being transferred from one chemical substance to another one. And that movement of electrons generates electrical energy. So you have oxidation happening, which is the loss of electrons. And since we have this electrochemical cell, this process, the oxidation, will be happening in the anode. So the anode is where the oxidation is happening. So you're generating electrons in that part. Oxidation is the loss of electrons. Whatever substance you have being oxidized is losing the electrons. So your electrons are being generated in that half. Then we have the other process, which is the reduction. And reduction is defined as the gain of electrons. The reduction is happening in the cathode. So the electrons are being generated in the anode where oxidation is happening, and they're being transferred or they're moving from your anode where the oxidation is happening towards the cathode. And then I will show you an example with a diagram in the next slide. So you have a potential, a cell potential associated with the chemical substance that you have that it's being oxidized, and another one that it's associated with the chemical substance that is gaining the electrons or it's being reduced. The difference in your potential is what's going to create this voltage between your two processes, the oxidation and the reduction. And that's what we're actually measuring. The difference between the oxidation and the reduction, those two halves, it's going to generate the voltage, which is the number that you're going to be measuring in this experiment. So you have a diagram in your lab book, and I made my own simplification here. I have two beakers, one on the left, one on the right, which are representing where the oxidation and the reduction is going to be happening. So you have an overall reaction, but if you have your overall reaction happening in the same container, your electrons are going to be transferred between your chemical species in the same container, and you're not able to actually measure that electrical energy that is being generated in your redox reaction. That's why we separate them. So we have a container for the oxidation, a container for the reduction, and then the electrons are forced to be transferred through a wire, and we can measure that potential. So in my representation, you have a solution. It's an aqueous solution containing ions. And then we're using a metallic electrode. So you have two metals. So I'm doing my diagram here between zinc and copper. Now I have my half reactions. You can see your half reactions in your lab book. You have a table with different elements and you have all of your reduction potentials for different elements in that table. So I'm just using the same ones that you have in the table, the one for zinc and the one for copper. We can actually calculate a cell potential for a chemical or a redox reaction using the equation that we have here. So with that equation, we can actually calculate the cell potential, standard cell potential for an electrochemical cell. So we can look at the table, we can find the potentials, we can calculate that E cell, which is just the electromotive force. Your electrons are being transferred, and the difference in your potentials for the cathode where the reduction is happening and the anode where the oxidation is happening is going to give you a voltage, which is the number that is expected. So I'm copying here my half reactions for zinc and copper, and I have my potentials for those two. I have one and another one. Now, if you want a spontaneous cell, electrochemical cell, you need to get a cell potential that is a positive number. So for you to get a positive number, you can arrange your potentials in the equation to give you a positive number. So you have the cathode minus the anode. My two numbers, the ones that I'm using for this example, it's negative 0.76 and 0.34. If you arrange your numbers in your equation, 0.34 minus negative 0.76, you're going to get a positive number. If you arrange your numbers in your equation, negative 0.76 minus 0.34, that's going to give you a negative number. If you get a negative number for the cell potential, your equation is representing a non-spontaneous redox reaction. Okay? For a spontaneous redox reaction, you have to get a positive number. So I'm going to put my numbers here. So you have positive 0.34 minus a negative number. So subtraction is the addition of the opposite, which means that you will get a positive voltage in this way. That will give you positive 1.1 units of volts. So between your copper and your zinc, you get that positive number. You get the positive number when cathode it's where the reduction is happening. So when your copper it's being reduced, copper plus 2, it's being reduced, gaining electrons, right? And the zinc it's being oxidized, losing electrons because that's your anode right there. You get a positive potential, and that represents a spontaneous chemical equation. So the half reactions that you have here, both of them are representing a reduction. Zinc plus 2, the ion of zinc gaining electrons, zinc plus 2 gaining 2 electrons to become zinc solid. That represents a reduction because reduction is gain of electrons. Same thing for the half reaction for the copper. You have a reaction that is representing a reduction, but if you want to write down your reaction that is representing the oxidation, it's just that same reaction but flipped. Looking at my calculation here, For you to get a positive number, you have to do 0.34, which is the potential corresponding for copper, minus your negative 0.76, which is the potential corresponding for zinc. 0.34 is in your equation in the cathode part. In your cathode, you have the reduction, which means that for that equation of copper, your equation is representing a reduction, which means that that part is correct. So the ion of copper, it's in solution. Remember, in solution you have the ions. The electrodes, it's a piece of metal, which is your element as a solid, a metal. So you have the ions of copper plus 2 in solution. The ions of copper plus 2 will be gaining electrons to become reduced, giving you the solid copper. Those electrons that the ion of copper is gaining because it's been reduced, they're coming from the oxidation of zinc. That represents your anode part, which is the oxidation. When something is being oxidized, it's losing electrons. So the zinc is the one that is being oxidized. Zinc plus 2, that's the ion of zinc. Plus 2 means that it lost 2 electrons, so the ion is not the one that is being oxidized because the ion it's already oxidized. So you see the reactions that you have in your table for your potentials, all of them represent reduction reactions. With the oxidation, it's just the same reaction in the opposite direction. Zinc solid goes to zinc plus 2 when it's losing 2 electrons. So I have my two half reactions. I have my potentials for each reaction, which I put my numbers in the equation to make sure that I get a positive number to represent a spontaneous reaction. Now, how this here relates to your diagram. If your zinc plus 2 is the one that is being oxidized, here on the first half, I have zinc as being oxidized. It means that zinc is losing electrons. The solid that you have here in your electrode is losing electrons. Those electrons are going to travel towards the other half where you have copper ion. The copper ion is going to get those electrons to become reduced. It's going to gain the electrons that the zinc is losing. When the electrons are traveling through your wire here, you get to see a number, which is the difference in your potentials. The potential for the zinc, the potential for the copper. That number will be something close to ideally 1.1. That's the expected number that we calculated. A spontaneous reaction, redox reaction between copper and zinc, you are expecting to get a potential that is close to 1.1. So when you actually do the experiment using this species here, copper and zinc, when the zinc is being oxidized, losing the electrons will travel towards where you have the copper ion to reduce the copper ion, and your voltage is the measurement that you're taking between those two half reactions.